this lecture we will see how to compute the manipulator Jacobian using a example of a robot manipulator. So, let us consider the robot manipulator shown in this figure, where the first joint is a revolute joint, that is theta 1, and the second joint A is a prismatic joint. It slides in the forward and backward direction. The third joint C is also a prismatic joint moving up and down, and the fourth joint E is a revolute joint. It is a rotational. The angle is denoted by theta 4. Now, using the DH procedure, we can fix the coordinate frames at each joint and then write the robot parameters as shown in this table. So, if the Z0 is the Z axis of the base frame and the Z1 is the sliding direction, Z2 is the sliding direction of the third frame, and Z3 is the revolute axis, the axis of rotation. The Z4, this is Z3, Z4 is the approach direction at the end effector. Then we can fix the X. X0, Y0 axis, and then the axes are fixed as the perpendicular direction to Z0 and Z1 is the Y direction, X direction, X1 and Y1 is the vertical direction, and similarly the X2 axis is parallel to X1 axis and the Y2 axis is the direction, this direction. Similarly, the X3 axis is parallel to X2 axis and the sliding direction is Y4, the perpendicular direction is X4. So, this can be this we have seen elaborately in the previous lecture on DH procedure. So, after this we can fix the joint angles. Joint angles are theta 1 and theta 4, and these are the two variables, and theta 2, theta 3 they are 0 here because the x2 and x1, x2 axis and x2, x3 axis are parallel. So, the angles between them are 0, and the joint distance D, OA is fixed here, and AC is the variable here, the sliding, the prismatic joint, AC is a variable, we can call it as D2, this is D1, and similarly CE is a variable, we call it as D3, and EF is D4 here. So, D1 and D4 are constants, D2 and D3 are variables here. So, there are 4 variables theta 1, D2, D3 and theta 4. And so, once the parameters are fixed in this using DH algorithm, then we can write the link coordinate frames, that is the ith coordinate frame with respect to the I minus 1th coordinate frame is the standard expression for the homogeneous transformation is given by this one, cos theta I minus sin theta I into cos alpha I, sin theta I sin alpha I into cos theta I, etc. So, this is the standard way of writing the coordinate frame I with respect to the coordinate frame I minus 1 here. So, using this we can write the Orm matrix, that is base the end effector frame with respect to base frame by multiplying all this 0 T 4 is the Orm matrix which relates the end effector frame, fourth frame with respect to the base 0th frame. So, that is 0 T 1, 1 T 2, 2 T 3, 3 T 4. So, this product will give the expression where we have to substitute various values given in the parametric table. So, now by substituting the parameter values we can obtain 0 T 1 as given here, 0 1 T 2. If you put I is equal to 2, we get 1 T 2 in the previous expression, and I equal to 3 will give 2 T 3 as given here, etc. So, the 4 matrix 0 T 1, 1 T 2, 2 T 3, 3 T 4 is obtained for the previous example in the by substituting the parameter values. So, now how to compute the manipulator Jacobian for this manipulator, this particular example. So, if you recall the manipulator Jacobian definition, it is the relation between the dxt, dyt, dzt, del xt, del yt, del zt. This is related with the Jacobian, it is a 6 cross n matrix. Here n equal to 4, the number of link is 4 here. So, 6 cross 4 matrix multiplied by the joint velocities, that is theta 1 the first joint variable and d2 dot, d3 dot, theta 4 dot. So, the general form is q1 dot, q2 dot up to qn dot. So, if a joint is revolute joint qi, that is equal to theta I, and if the revolute joint is prismatic, we denote it by di. So, the velocity of the joint velocity at each joint is given by the derivative of these variables. So, theta I dot represent the angular velocity at the joint I if it is a revolute joint, and di dot denotes the linear velocity if it is a prismatic joint. So, the relation between the joint velocities and the end effector velocity with respect to itself. Here dxt, dyt, dzt represent the linear velocity with respect to the x, y, z axis of the end effector frame, and del x, del y, del z, this t superfix t represent the rotational velocity of the end effector with respect to the end effector frame. So, this are related. So, how to find the Jacobian matrix J 6 cross 4? So, that we have seen in the previous lecture as the following. So, the J 6 cross n matrix in general, how it is calculated? It is calculated by the following formula. It is minus nx p y plus ny px minus ox py plus oy px minus ax py plus ay px, and n z del dot n. So, n Z, O Z, A Z. So, this is the first column. Similarly, we can calculate the second column. If it is revolute joint, and if it is a prismatic joint, we will get N Z, O Z, A Z 0 0 0 if prismatic. Now, what is this N, O, A, P, etc. this notation? As we have seen in the earlier lecture, if you have a homogeneous transformation T, the first column is denoted by N vector, second is O vector, third is A vector, fourth is the vector P, and 0 0 0 1. The ith column of the Jacobian matrix is computed using the matrix I minus 1 T n, where n is the number of link for the manipulator. In this example, n equal to 4. So, if you want to calculate the first column of the Jacobian matrix, we put I equal to 1, it means 0 T 4, 0 T 4, if you call it as T, then we have the first column as N, O, A, P, etc. that can be substituted in this formula. Because the first joint is the revolute joint, this formula will hold good. Now, if you want to calculate the second column of the Jacobian matrix, we put I equal to 2. So, we get 1 T 4. So, if you take 1 T 4 that as the T matrix, for 1 T 4 the how to calculate 1 T 4, it is 1 T 2, 2 T 3, 3 T 4. If you multiply this 3 matrix as given here, that is 1 T 2 multiplied by 2 T 3 into 3 T 4. This product, it will give the matrix 1 T 4. So, from that we select the N, O, A, P columns and then substitute in this second value, because this formula is for the prismatic joint that we have seen in the previous lecture. Similarly, the third column, it is a prismatic joint. So, that is 2 T 4 to be calculated. From that we make use of the similar expression for the third column. Then the fourth column is 3 T 4. 3 T 4 is already given here. So, the first column is N, second is O, and third is A and P. So, substituting this in this formula, because the fourth is the revolute joint, the same formula as given in the first column is valid. Only thing is the NOAP is calculated from 3 T 4. So, the procedure for calculating the Jacobian matrix is in this manner. So, we can actually calculate all of them. Now, 3 T 4 is given as it is for the parameter values. So, let us assume that the length is OA is 10, BC is 12, DE is 6, EF is 4, etc. So, these values are given, and AC and CE, these are the variables, because the joints are prismatic joints. So, substituting the values in this expression, we get the values to be like this. The calculation of 3 T 4, 2 T 4 1 T4 and 0 T4. So, this is used for first column of the Jacobian and 1 T4 is for the second column. This is for third column and this one is for the fourth column of the matrix. So, using that we can get the Jacobian matrix. So, the Jacobian matrix is calculated at every instant of time. Actually, when the robot is moving to various positions, at a particular position what is the value of the Jacobian, that can be calculated, because all this theta 1, d2, d3, theta 4 are varying. So, as they are changing, what is the Jacobian matrix? So, at a particular instant of time, let us say the end effector is in this configuration. The end effector coordinate frame with respect to base coordinate frame, this is 0 T4 is given by this expression. Now, 0 T4 is calculated by the last expression, 0 T4 is given. So, if you compare each element 0 T4 with the required configuration of the end effector, and then we can easily solve the equations. There are 12 such equation, we can solve them, most of them are 0 here. So, it is very easy to solve just by comparing 0 T4 expression with the constant matrix, and then we will get this configuration. That is when theta 1 minus theta 4 is pi by 4 and we get the values d2 to be equal to 6 and d3 4 etc. So, these values are obtained directly by solving the inverse kinematics solution of this particular configuration. So, at this value what is the manipulator Jacobian? So, that is calculated by the following. So, now let us calculate. So, the first column of the manipulator Jacobian. So, it is actually given by the values minus nx py plus ny px minus ox py plus oy px and n z oz az. So, this is using 0 T4 columns at that particular values. So, we can substitute here directly by seeing nx, py etc. from the expression given here. In 0 T4 we can see that nx is cos of theta 1 minus theta 4 and py is minus d2 cos theta 1. So, this plus ny px, ny is sine of theta 1 minus theta 4 and px is d2 sine theta 4. If you multiply and add, substituting in this formula, we will get the value to be d2 cos of theta 4. Similarly, we can see from the matrix 0 T4 these values, we will get minus d2 sine theta 4, then 0, 0, 0 and minus 1, that is n z. From here we can see that the third value nz is 0, oz is 0 and az is minus 1. So, this is substituted here 0 0 minus 1. So, the first similarly we can calculate the second column of this thing. The second column is, it is given by n z o z a z 0 0 0. It is using 1 T 4. Because it is a prismatic joint, we have this expression. So, 1 T 4 if we see here, n z is sin theta 4 and o z is cos theta 4 and then 0. So, we can substitute those values here. So, we get sin theta 4 cos theta 4 0 0. So, this is the second column. So, similarly we can calculate the third, fourth column etc. of the manipulator Jacobian. Now, having computed the manipulator Jacobian, so what we get is the left side we have the linear velocity and angular velocity. If we denote the linear velocity to be, so let us say the velocity, linear velocity and the angular velocity dxt, dyt, dzt, we call it as v, and del xt, del yt, del zt, call it as w, angular velocity with respect to the end effector frame. It is equal to Jacobian multiplied by this q1 dot, q2 dot etc., qn dot in the general case. So, we can denote it by v is equal to jq. For example, in the simple notation, v is the left side, j into q is the vector given as q1, q2, qn dot. This is the expression. Now, we can calculate q dot to be, if j is a square matrix, then we can take the inverse of j. But normally in this example, for example, here it is 6 cross 4 matrix. So, in general it is a 6 cross n matrix. So, we may not get a inverse of j generally, but we can get the pseudo inverse. We call it as the pseudo inverse of the non square matrix, we can write. So, that is given by, this is equal to j transpose j inverse into j transpose, sorry, into j transpose. So, we can see in this example, if j is 6 cross 4 matrix, then j transpose j is a 4 cross 6, 4 cross 4 matrix. So, it is a square matrix and we can find the inverse of j transpose j and multiply it with j transpose. So, this expression is called the generalized inverse of a matrix, whether it is a square matrix or non-square matrix. So, we can calculate the q dot value using this particular formula, the expression given here. So, if the end effector velocity v is given with respect to the end effector frame, then how much of the velocity of the actuators to be given at each joint is calculated by this particular formula. So, similarly, by generating the ARM matrix and making use of the formula as described in this lecture, we can calculate the manipulator Jacobian for various types of manipulators. Okay, thank you.